Alright guys, welcome to section 4.3. In section 4.3, we're interested in the idea of optimization. Optimization is a way to basically use the least material to accomplish a specific task. So like for example, say if you want to build a car that goes 100 miles in as little gas as possible. In that simple example, we call that problem an optimization problem because we're trying to build a car that can go 100 miles using as little gas as possible. And cars are actually becoming a lot more efficient. So that it's absolutely something that is doable. Nowadays you can see like sorry about that. Nowadays you can see like Prius, especially the Prius plug-in, it can go 100 miles in 1 gallon of gas. That's pretty optimal to me. Alright, so let's start out with some simple examples and I'll show you how these can be done using the first derivative. Alright, so say if we want to build a container, a cylindrical container that can hold 40-inch cube of juice, and we want to use as little material as possible to develop this can. So here is a typical example of what it looks like. We want to build that to hold 40 cubic inch of juice using as little material as possible. Means that we want to minimize the radius, and we also want to minimize the height. Alright, so what is the dimension that will allow us to achieve this task? Alright, so we start off by first determining the formula of what we want to minimize. So basically in this case we want to minimize the material is really the surface area. So we want to minimize the surface area, which can be expressed as follows. So the surface area of a cylinder is, so I'm going to use the letter S, is equal to, basically what you do is you take the area of the base times the height. So, I'm sorry, not the area of the base times the height. That gives you the volume. The surface area is basically the area of the bottom and top, which are two circles, so it's going to be pi r squared. But because there are two of them, we go ahead and double that. So that would be the surface area for the two, the top and bottom. And we're going to add that to the area outside the cylinder, which can be found by taking basically if you cut this out and you lay it flat, it will look like a rectangle. This rectangle will have a height of h, and it will have length of 2 pi r, which is the circumference of the circle. So the area of that part will be multiplying the height and the length, which is going to give us 2 pi r(h). So 2 pi r(h). So that's the formula for the surface area of the cylinder, which is what we want to minimize. We want to minimize the surface area. So you want to start with the formula for whatever you want to minimize. Alright, and then what you want to do next is you want to look at the given information and see what we can use these given information for. So the given information here is basically, it says that the volume is 40 of the cylinder. So you want to start off with the volume, with the formula for the volume, which is pi r squared times h. Now we know that the volume is 40, so we're going to go ahead and replace 40 in for the volume, and this is what we're going to get. Alright. Now you might wonder why, how is this information going to help us minimize the surface area? Well, right now the formula for the surface area involves two variables, which are r and h. we want to use this additional information to somehow reduce the surface area formula down to just either R or H. And to accomplish that task, we can basically solve for what H is and then plug it in here. If we solve for H, you're going to see that H equals to 40 pi R squared. Plugging this into that H, we have the surface area equaling to 2 pi R squared plus 2 pi R. And then remember, I'm replacing 40 over pi R squared in for the letter H. Simplifying the equation will give us 80 pi. The pi is going to cancel out, so 80 is good. 80 over the R. One of the R's will cancel out, so we have 80R. All right. So look, we started with surface area involving two variables. We were able to use additional information from the problem to remove one of the variables. And now we know that the surface area can be described in terms of the radius of the cylinder. So to minimize or maximize, now we think of this as a function, and to minimize or maximize the function, we basically take the first derivative with respect to R. So S prime of R is 4 pi R minus 80 over R squared. All right, so the derivative of that is going to be negative 80 over R squared. We're going to go ahead and find the critical point by setting this equal to 0. All right, and then we're going to go ahead and clean up this mess a little bit and solve for R. So I'm going to move this to the left. We get 80 over R squared equals to 4 pi R. Go ahead and cross this out. We can basically if we kind of clean this up a little bit more, we're going to see that R cubed is equal to 80 over 4 pi. All right, and then from solving for R, we're going to see that R so basically what we're going to do now is we're going to raise both sides by 1/3, but why don't we reduce this first? So 4 does go into 80, and that gives us 20 pi. All right, so 20 over pi equals to R third. And now to find R, what we do is we raise both sides by 1/3 like this. Okay, so I raise both sides by 1/3, and so I have R. So R equals to 20. Sorry about that. R equals to 20 over pi raised to the 1/3. Okay, so this point right here, which is about 1.85, is our critical point. In other words, this is the point where the minimum surface area is going to take place. And remember, we're asked to find dimension. So once you find the radius, you also need to find the height of the cylinder, because we're asked for the dimension. So here's the radius. To find the height, all we have to do is plug this back into the R right here. Okay, so the height is equal to 40 over pi, and then I have to replace that in there. And remember, R is equal to 1/3 like this, and then I square it because it's R squared. This is R. All right, that's R, and then I square it. This will clean up pretty nicely. We get 40 over, not too nice, but it's manageable. We're gonna get 40 over pi times 20 over pi to the 2/3, 2 over 3, and that's H. That's the height that will basically minimize the surface area while maintaining 40 inch cube of volume. Now, if we break this down into numbers where we can understand, this is about, that is about 1.85 inch. So maybe I'll do that. And then H, if you work out the detail for H is about 3.7 inch. All right, so that is the dimension that basically minimizes our surface area while maintaining 40 inch cube of volume. So to kind of recap how we optimize any types of problems, we start off with a formula of what we're trying to optimize, either maximize or minimize. And then usually this formula will involve two variables. What we're going to do next is we use additional information to somehow write one variable in terms of the other, so that when we make a substitution into our first formula, one of the variables will disappear, so that we can easily take the derivative to find the minimum or maximum of the desired value. All right, so great job on that first problem. Let's go ahead and turn over and let's do a couple more. All right, so taking a look at this problem, the first thing you want to do is you want to really understand the problem really well. I'm going to change a few numbers here just so that things can work out a little bit better. Let's make this a 6, and that's also a 6. Okay. All right. So here's our challenge. We want to be able to find the radius and the height of this cylinder so that it can have as largest volume as possible that can be inscribed in a right cylinder. So the cylinder has to fit inside this right cylinder cone, but we also want to make this cylinder to have as large of a volume as possible. So again, remember, you always start out with the formula that you want to maximize. In this case, we want to maximize the volume of this cylinder. So just so that we label this a bit clearly, this is the radius of the cylinder, and then clearly this is the height of the cylinder. All right, so let's call that H. Okay. The volume of a cylinder, so start off with the formula of whatever it is that you want to maximize. In this case, it's this volume. So I will go, the volume of a cylinder is going to be, remember, it's the area of the base, pi r squared, times the height. That's how we find the volume of a cylinder. All right. All right, so notice that it involves two variables, r and h. So our next step is to use whatever additional information we have and try to remove one of the variables. So here's what I know. If you encounter a problem that involves, anything in terms of a pyramid, in terms of a right cylinder cone, then you can use a property in geometry called similar triangles. So here's what I'm going to do. I know that, so I'm going to just kind of chop this in half, and if you chop this in half, then you get a triangle that looks like this. Okay, so, and then it goes like that, and then it goes like that. Right, so remember, this base, the radius from here to here is 6. The height is 10. The height of the whole thing is 10 from here to here. From here to here is 10. Remember, I'm chopping this in half. All right, and my radius is somewhere in the middle. So if you chop this in half, if you look at similar triangles, then here's the radius. All right, so that's the radius. Okay, and then remember, I call the length from here to here h. That means from here to here is considered h, and 10 is just the overall length. So let me erase that so that you get a better feel for that. The overall length is 10. All right. So if the overall length is 10 and the length from here to there is called h, then that means that this leftover piece has to be 10 minus h. Okay. So what you're looking at here is you're looking at two similar triangles, and we know that two similar triangles are proportional to each other. In other words, if you take the length or the height and the base of the large triangle, in other words 10 over 6, then that will also equal to the height of the smaller triangle, which is this guy, 10 minus h, over the base of the smaller triangle, which is r. So that's their relationship, which gives us the relationship between h and r. So if we want to write this formula in terms of r, then we have to solve for h. So we solve for h, then notice that 10 minus h will equal to, remember 10 over 6 can be reduced to 5 over 3, and if you cross multiply you get 5r over 3, and that would mean that h is equal to 10 minus 5r over 3, which is kind of nice because now if we take that and plug it in here, then everything is in terms of r. Alright, so let's go ahead and do that. So we found our relationship, we plug that in there. So the volume is equal to pi r squared times 10 minus 5r over 3. Distribute 10 pi r squared minus 5 pi r cubed over 3. Alright, we have expressed the formula of the volume of our cylinder in terms of just r. Our next step is to go ahead and take the derivative so that we can find the maximum, because the maximum always takes place at the derivative. In other words, when we take the derivative, we're finding an r that would produce the maximum volume. Alright, because that's what we want to do. We want to maximize the volume. So let's go ahead and take the derivative with respect to r. That would be 20 pi r minus, how nice is this? The 3 is going to cancel out once that's brought down, so you have 5 pi r squared. Alright, go ahead and set this equal to 0 to find the critical point where the max will take place. I'm able to factor that out. I have 4 minus r. So you got two possibilities. Here's one factor, here's another one. So r either equals to 0 or r equals to 4. Knowing for sure that the radius of a cylinder can't be 0, then we know that r equals to 4 is the radius that would maximize the volume. So what is the height of this cylinder? Well, we know the relationship to find the height, which is 10 minus 5r over 3. So now what we do is we take this and we plug that in there. Alright, so the height is 10, take away 5 times 4 over 3, 10 minus 20 over 3. We can think of this as 30 over 3, which once we simplify, we get 10 over 3. Alright, so we're done. So the height and the radius that maximizes the volume of the cylinder is r equals to 4 and h equals to 10 over 3. Now I can tell you that as I'm walking you through this problem, I'm sure you're going to run into a lot of trouble, which is completely normal. But I do suggest that you re-watch the video, and it's okay even if you did example 1, 2, and 3 again and again and again, because the more you do it, the more opportunity you're exposing your brain and you're letting it synthesize the information that you just gain. And the more you expose yourself to a particular example, even though it's the same example, you're just going to improve. Alright? So give yourself a chance and do that if you didn't completely understood what everything that I did in example 2. Alright, last problem, example 3. We're given a box, and basically this box is to hold an 8 centimeter cube of something, of feet, inch, whatever it is. And we want to minimize the surface area. In other words, we want to use as little materials as possible. Say you're wrapping a present, and inside the present is something that is, and you want the space to be 8 centimeter cube. All right. So what is the minimum paper that you can use, which is surface area? All right. So we start off by what we want to minimize. In this case, we're going to minimize surface area. So let's develop a formula for the surface area. Notice that the box has 4 sides. Each side has an area of, this is y. So it's y times x is the area of that side, and there's 4 of them. So you know that there are, you can go ahead and find one and then add 4 times 4. And then you have the top and the bottom, and the top and bottom are both x and x. Or in other words, the area for the top is x squared, the area for the bottom is x squared. So in other words, the surface area, which is what you want to minimize, is the top and the bottom, which is, there's 2 of them, so x squared, x times x, plus, and there's 4 sides, right? So you go 4xy. That's what we want to minimize, right? Now, the next thing we do is we look for a way to remove one of the variables. The additional information that you find in the problem will help you do that. So it says volume is 8 centimeter cube. So you go volume, and first you got to know how to find the volume. It is, you know, length times width times height, which is x squared times y. And knowing the volume is 8, you replace 8 in for the volume, and this allows you to figure out what is y. Okay, knowing the relationship between x and y, go ahead and take that and plug it in there, which allows you to reduce your formula for the surface area down to just in terms of x. So s equals to 2x squared plus, those cancels out, you're gonna get 1 over 2 x cubed. Alright, max or min, in this case we're gonna minimize. So minimize always occur at the vertex, or I'm sorry, another way to say that is minimize always occur where the first derivative equals to 0. So go ahead and take the derivative with respect to x. 4x plus 3 over 2 x squared, set that equal to 0. Factor out an x, 4 plus 3 over 2x. Alright, so you got 2 options. You either have x equals to 0, or you have x equals to x equals to negative, I'm trying to cheat myself here. Now, x can't be a negative number, and so that does not make sense, because how can you have a volume with a negative number? So that doesn't make sense. And I think I know why. This is my mistake and not yours. This should have been 8 over x squared. Okay, so look over here. This should have been 8 over x squared. That's why. So replace this. Sorry about that. It's going to change a lot here. 8 over x squared. I'm just going to erase everything here. Okay. Plus, and then what you're going to get here is you're going to get 32 over x, okay, and then take the first derivative, 4x minus 32 over x squared, set this equal to 0, okay, move the 32 over x squared over here, 4x, alright, we're going to multiply everything by x squared, 32 for x cubed, divide both sides by 4. 4 is going to go into 32 8 times. So x equals to 2. Awesome. Alright. So guess what? The dimension that minimizes the volume, I'm sorry, the surface area is x equals to 2, but then we have to find y. So here's the relationship to find y. We're going to go ahead and take this and plug it in there, and that helps us calculate y. Alright, so y equals to 8 over 2 squared, which means that y is also equal to 2. Alright, there you go. I will see you guys tomorrow.